Right, today we begin a new topic, and that's condensations and alpha substitutions of carbonyl compounds. The last experiment we did in lab, which was the preparation of dibenzyl acetone, is an example of this. Right, this is the general mechanism for alpha substitution. Okay, some kind of a base removes an alpha hydrogen. An alpha hydrogen is on the carbon next to a carbonyl. Okay, although this anion now is resonance stabilized, it's actually the carbon that attacks the electrophile. And we replace that hydrogen with this electrophilic group. Okay, this is called an enolate ion. Okay, so here is an example of the condensation of an enolate with a ketone. Okay, we form the enolate, and this nucleophile then attacks the carbonyl carbon, and the oxygen, okay, which gained a pair of electrons and became negative, then picks up a proton, and we get our addition products. Okay, this addition product now is a beta hydroxy carbonyl compound. Okay, and this goes back to the idea from our chapter on aldehydes and ketones, that aldehydes and ketones tend to undergo addition. Okay, now when you have an ester as your electrophile, the enolate again attacks the carbonyl, but instead of undergoing a protonation at this oxygen, which would form an unstable hemiacetal, what happens is the oxygen pushes down and it kicks out this alkoxide. And instead of a beta hydroxy carbonyl compound, what we get is a beta carbonyl compound. Okay, so this is a substitution product rather than an addition product. Okay, under neutral conditions, in most cases, enols are not favored. Okay, there are some exceptions, but generally the ketone form is going to be favored. And this equilibrium is called tautomerization. It's the interconversion of isomers that occurs through the migration of a proton and the movement of a double bond. These are not resonance structures because we've moved a hydrogen. Okay, under basic conditions, okay, such as when you're using hydroxide, hydroxide removes the alpha hydrogen, and although the equilibrium does not favor the enolate when you're using hydroxide, you do get some formation of this enol form. Okay, an enol is when an alcohol is directly attached to an alkene or a vinyl alcohol. So in the presence of strong bases, ketones and aldehydes can act as weak proton acids. Proton on the alpha carbon is abstracted to form a resonance stabilized enolate ion with a negative charge spread over the carbon atom and the oxygen atom. The equilibrium still favors the keto form over the enolate anion. Okay, under acid conditions, okay, first we have a protonation that occurs, and this time we have a protonated carbonyl. It's resonance stabilized, and water then removes this alpha hydrogen and we can form an enol. Okay, because of enolate and enol formation, we can end up with racemization when we originally had an optically active starting material. Okay, so here we have actually 3 alpha hydrogens, and under acidic or basic conditions, we form this enol, which is now achiral. Okay, and that's because it's flat. There's a plane of symmetry in the plane of the screen here. Okay, that can equilibrate back and forth between the R and the S. This reaction is regioselective. So with a weaker base, such as hydroxide, we get the more substituted enol. With a very strong base, okay, something like tert butoxide or lithium disopropylamide, then we will get the less substituted enol. For aldehydes and ketones, the keto form is still greatly favored at equilibrium, but you still have this equilibrium and ultimately racemization that occurs. Okay, let's look at the acidity of alpha hydrogens. The pKa for the alpha hydrogen of an aldehyde or ketone is about 20. The pKa for the aldehyde hydrogen, that is not acidic at all, but the alpha hydrogen is. Okay, so back here, okay, when we're removing an alpha hydrogen, this formation of the enolate ion is not favored because water is 15.7. This is about 20. And so we're making a stronger base from a weaker one. So this equilibrium favors the starting material. These alpha hydrogens are much more acidic than alkane or alkene hydrogens, which typically are greater than 40, or alkyne terminal hydrogens, which are about 25. Okay, but only a small amount of the enolate ion is present at equilibrium. Okay, because again, we're trying to make a stronger acid, water, from a weaker acid. So that's not favorable. Okay, so here, and that's what this is showing, except we're using an alkoxide, which is the conjugate base of an alcohol, which typically is about 16 to 18. Okay, so the equilibrium, again, does not favor the enolate. Okay, here's a specific example. For cyclohexanone, the pKa of the alpha hydrogens is 19. For ethanol, it's 15.9. And going back to this previous slide, the reason that these alpha hydrogens are more acidic than ordinary alkane or alkene hydrogens is that this enolate ion is resonance stabilized. Okay, so here is the energy diagram for substitution. Okay, so the first step, okay, that is formation of the enolate ion, is endothermic. It's slow. It does not favor the enolate. But if there's an electrophile present, this reaction occurs rapidly. Okay, low activation energy, and it's also thermodynamically favorable. This next step is exothermic. Okay, so here's a very strong base. This is called LDA, which stands for lithium diisopropylamide. We start with diisopropylamine and reacting it with an even stronger base, butyl lithium. We get butane, and then we get LDA. Right, when LDA is used, this goes all the way to the enolate. Okay, because pKa of the amine is about 36, whereas the pKa of the alpha hydrogens on the cyclohexanone is about 19. Okay, so this is very favorable. It goes all the way to products. Okay, here we'll talk about alpha halogenation of ketones. Okay, under basic conditions, if we have an alpha hydrogen, the hydroxide removes that alpha hydrogen, which then attacks the halogen. So we get an alpha halo ketone. Okay, this reaction is actually called base promoted rather than base catalyzed, because it actually does use a full equivalent of base. And we can see that the base is not regenerated. Okay, so here is the base promoted halogenation. Hydroxide removes this alpha hydrogen. We have our enolate anion, which then attacks the halogen. Okay, typically chlorine, bromine, or iodine. Okay, the byproduct is a halide ion. Okay, if there's more than one alpha hydrogen, then we can have multiple halogenations under basic conditions. Okay, the alpha halo ketone is actually going to be more reactive. Okay, so the presence of this nearby chlorine is going to render this hydrogen more acidic than if the chlorine weren't there. And so this undergoes a second reaction. And then we have halogen substitution on the other side. And then the same thing is true of this remaining hydrogen. This is now even more reactive than it was when the chlorine was not present. Okay, and so the second halogenation can occur faster. It does occur faster than the first. Okay, and because of the tendency for multiple halogenations, this base-promoted halogenation is not widely used to prepare monohalogenated ketones. Okay, so if you have more than one alpha hydrogen, it's nearly impossible to stop at just one halogenation. Okay, if we have three alpha hydrogens, that is, if we have a methyl ketone, okay, what we have is the haloform reaction, and specifically if it's bromine, it's called the bromoform. But you can do this with chlorine, bromine, or iodine. Okay, so if we have hydroxide and excess halogen, all three of these hydrogens get replaced by the corresponding halogen, and this trihalomethyl ketone is not isolated. Instead, what happens is we'll get a carboxylate, and then we'll get a trihalomethane or a haloform. Okay, so here's the mechanism. The carbon with these three halogens on it is now significantly electron withdrawing, so that makes this carbon more electrophilic. So hydroxide attacks, and the trihalomethane anion is removed, which immediately grabs an acidic hydrogen from the carboxylic acid. Okay, so we get our haloform, we get our carboxylate ion. Okay, so when chlorine is used, chloroform, CHCl3 is formed, bromine forms bromoform, and iodine forms iodoform. Okay, this is actually a useful simple chemical test when we use iodine, and we've done this many times in the past in the laboratory. Okay, so with iodine and with hydroxide, okay, we get substitutions of all three of the alpha hydrogens. And actually, if we have a secondary methyl carbonyl, secondary methyl alcohol, this actually gets oxidized to the corresponding ketone. And iodide gets reduced to iodide. Okay, so with excess iodine and hydroxide, okay, all three of these hydrogens get replaced. Hydroxide comes in, kicks out Ci3 minus, which then grabs a hydrogen from our carboxylic acid. Okay, where this is useful is that when you're using iodine, the product is actually a yellow solid, whereas with bromine and chlorine, it's a liquid. Okay, so iodoform forms a pale yellow precipitate, and this is a simple chemical test for a methyl ketone. Okay, so in this problem, it says to propose a mechanism for the reaction of 3-pentanone with sodium hydroxide and bromine to give 2-bromo 3-pentanone. Okay, so what happens here is hydroxide removes the alpha hydrogen. We have our resonance stabilized enolate. The alpha carbon anion attacks the bromine, and then we get our alpha haloketone. Now, under basic conditions, this is going to keep going. Okay, in fact, we'll if we have excess bromine, we can replace all 4 of these alpha hydrogens with bromine. Okay, so if this is your target molecule, this is really not a good way to do it. Okay, now if we do this under acid conditions, we can, in fact, stop at just 1 halogen substitution. Okay, so here we have acetophenone. And with acetic acid and bromine, we get the alpha bromo acetophenone in 70% yield. And it turns out that this doesn't react further, so we can stop at just 1 halogenation. This, by the way, is an ingredient in tear gas. Okay, it's a very irritating compound. Okay, so acidic halogenation may replace 1 or more alpha hydrogens depending on how much halogen is used, but this is a good way to achieve mono substitution. Okay, so acetic acid serves as both the solvent and the acid catalyst. Okay, so how does this work under acid conditions? Okay, we form the enol. Okay, we had this mechanism earlier. We form the enol. Oxygen pushes down, the alkene group attacks the halogen. We get our alpha substituted carbocation or cation intermediate. And then the halide comes in and removes the enol hydrogen. This pair of electrons then moves down and we restore the ketone. So we get our alpha haloketone. So the mechanism of acid catalyzed halogenation involves attack of the enol form of the ketone on the electrophile halogen molecule. And loss of a proton gives the haloketone and the hydrogen halide. Okay, so let's look at the mechanism for alpha substitution on cyclohexanone under acidic conditions. Okay, so first we have formation of the enol. The oxygen undergoes protonation. We have our stabilized intermediate. The acetate ion removes an alpha hydrogen. That gives us back our acetic acid. We get the enol form. Oxygen then pushes down. The alkene attacks the chlorine, and then chloride removes this hydrogen, and we get our alpha chlorinated cyclohexanone. All right, this is the Hell-Vollard-Zelinsky, or HVZ reaction. Right, so this uses phosphorus, tribromide, and bromine. You can also do this with chlorine and PCl3. But when these react, you form an alpha bromo acyl bromide. Okay, in the last chapter, we talked about acyl halides, but we get bromination here and at the alpha position. Okay, in the presence of water, okay, what happens is the acyl bromide gets hydrolyzed. Okay, it's much, much more reactive than the alpha bromide. And we can get an alpha bromo acid. The acid is treated with bromine and phosphorus tribromide. It's followed by hydrolysis. Now, historically, the HVZ reaction was used to prepare amino acids, which are building blocks of protein. Okay, so if you react this with excess ammonia, you can bring about a substitution where the bromine is replaced by an amino group, and nearly all of the naturally occurring amino acids are alpha amino acids. The downside, though, is that this reaction and the substitution using ammonia are not stereoselective, so you're going to get a racemic mixture. Whereas if you want to synthesize proteins, they have to be optically active in most cases. Okay, so with Br2 and PBr3, we form the acyl bromide, and this undergoes equilibration between the keto and enol form. And the enol form serves as a nucleophilic intermediate. The acyl bromide enolizes more easily than does the acid. Okay, so once we form the acyl bromide, then we form the enol, and once again, just like with the formation of alpha haloketones, oxygen pushes down, the alkene group attacks the bromine, bromide removes this hydrogen, and we get our alpha bromo acyl bromide. Okay, so when we add water, the acyl bromide is much more easily hydrolyzed than the alkyl bromide.